Yes, members, welcome once again to this yet another new interesting lesson about modern physics. In today's lesson, I'm going to be looking at radioactivity and ionizing radiations. So, by the end of this lesson here, I expect that every one of us must be able to define the term radioactivity, state the types of ionizing radiations and differentiate them, state any applications of radiations, state any dangers of radiations, and state any safety precautions while handling radioactive materials. That is what I expect every of us to get by the end of this lesson here. So let's begin. Ionization. What is ionization? Now, assume that, for example, throw a stone at a very high speed towards a watermelon. What do you think happens? Okay, yes, it splits up into different parts. So what we call ionization is almost the same as that. That is a good analogy of what we call ionization. In other words, ionization is coming from two words, from a word called ion. Note this ion here, this is a metal, but this ion here. And we have two types of ions. We have what we call a positive ion and then a negative ion. Now, the word ionization occurs when an atom loses or gains one or more electrons. And at the beginning, we said that when an atom loses or gains an electron, it becomes charged. So when an atom loses electrons, it becomes positively charged. Why do we say this? It is because it has lost the negative charges. So it remains with more of the positives, like we saw in electrostatics. For example, have this lithium atom here. How many protons does it have from what we discussed previously? So protons are 3. How many electrons does it have? Okay, electrons are also 3. And how many neutrons does it have according to the diagram? It is 4. Very good. So in this, we have positive, we have a charge of positive 3. We have a charge of negative 3 on that atom there. So this one is electron and neutron. Now when this one here loses an electron, in other words, when this electron here goes away, it remains with 2 negative charges, but the positives remain there as 3. So this one is having a net positive charge. So when an atom loses an electron, it becomes positively charged. It gains an electron, it becomes negatively charged. So what we call ionization is simply the process of making an atom to either become a positive ion or a negative ion. The process of ionization is simply making an atom or molecules to become ions, positive and negative ions. So that is what ionization is all about. Now, about radioactivity and ionizing radiations, what are these? First of all, in the previous lesson, we said that an atom which is massive, in other words, a heavy atom, has very many protons and neutrons in the nucleus of an atom, and in many cases, they are unstable. So when they decay, they give off radiations that cause ionization. So this phenomenon is called radioactivity, and the radiations produced are what we call ionizing radiations. And we need to note that radioactivity is a random process. We cannot determine that if this nucleus has decayed, has undergone radioactivity at this time, it is going to decay at the same time, it is going to decay again after a given time. No, we cannot tell that. So it is a random process. The person who discovered radioactivity is shown in this diagram here, and he did this in 1896. You can Google more about him. It's called Henry Becquerel. So Google about him and find out more about that. So let's begin taking some notes. Radioactivity. What is radioactivity? This is a spontaneous disintegration of unstable radioactive nuclei with the release of energy. It is a random, it is a spontaneous disintegration. We've just said that it doesn't, you cannot predict it. So when defining this, please make sure that you talk about spontaneous disintegration. You talk about unstable nuclei, and then release of radiations. And these radiations are what we call the alpha, beta, and gamma radiations. Let's watch this video about these three.
The nucleus of radioactive material emits three different types of radiation rays, called alpha, beta, and gamma. Due to the distinct electrical charge characteristics of the alpha, beta, and gamma rays, they can be separated by directing a beam from a radioactive source through a magnetic field. Alpha rays carry particles originating from the nucleus of a radioactive atom. These particles consist of 2 protons and 2 neutrons. Essentially, they are positively charged helium atoms stripped of their electrons. The magnet causes these particles in the alpha ray to bend in one direction. Beta rays are a stream of negatively charged electrons. After passing through the magnet, they bend in the opposite direction of the alpha ray. Because electrons of the beta ray have less mass than the protons and neutrons in the alpha ray, the beta ray undergoes a more pronounced bend. Gamma rays are pure energy. Because a gamma ray has neither mass nor charge, it remains unaffected by the magnetic field. The unique characteristics of these three types of radiation affect their capacity to penetrate various materials. Whereas an alpha particle is stopped by a sheet of paper, a beta particle easily passes through paper but is stopped by aluminum. A gamma ray is not impeded by the paper nor aluminum, but its progress can be stopped by lead. The degree to which each of these three forms of radiation penetrate human tissue is the basis for limiting a person's exposure to radioactive material. In terms of the impact of radiation on the human body, alpha particles are generally stopped by the outer layer of skin and pose no real harm to underlying tissue. Beta particles, however, are not stopped by the protective layer of skin and can damage deep sensitive tissue. Gamma rays likewise can penetrate deep into the body and cause harm. This is why it is necessary to wear specialized protective gear when working with radioactive materials.
So there are three types of radiations emitted from an unstable radioactive material, and these are what we call the alpha particles. Normally use this letter here, alpha particles. We have the beta particles. We normally use this letter here, beta particles, and then the gamma rays or radiations. Note that alpha and beta are particles, but gamma are simply rays. They're just radiations. So how do we distinguish them? We can start by talking about each of them, then we shall then look at the differences between each of them. Please take some notes as we move on along the way. So an alpha particle consists of 2 protons and 2 neutrons. In other words, an alpha particle is taken to be the nucleus of a helium atom. And we represent this using the helium nucleus like this. Remember, it is having 2 protons and 2 neutrons, meaning that the atomic mass is a 4. Remember that. So that is an alpha particle. So since it is having protons and neutrons, then it is having a mass. Then it is strongly ionizing, meaning that once it meets other atoms, it can disintegrate them, it can ionize them, forming positive and negative ions. Another particle is what we call a beta particle, and a beta particle is simply a high-speed electron, simply an electron that is moving at a very high speed. So we represent this using an E, and it is having a representation of this, that is an electron. And At higher levels, we shall find out that this is produced when a neutron has decayed into an electron and a proton. But at this level, this is not very important to you. All it knows that a beta particle is a fast moving electron and it is moderately ionizing. Lastly, we have the gamma rays. These are high frequency electromagnetic waves. And since they're simple rays, they have zero mass, or we can simply say that they don't have any mass. They're just radiations of energy. So those are three radiations emitted from a radioactive material. So let's try to compare the types of radiations. Let's try to tell the differences. What are the properties of each of these using this table here? And I need you to first of all pause the video, try this one out, then play again later on. Okay, so let's check our work, what you've done there and what is correct. So alpha particles, beta particles, gamma rays. What is the difference between all these radiations here? First of all, the alpha particle is a helium nucleus in nature. It is a helium nucleus in nature, meaning that we can represent it like this. So we have 4, we have a 2. And then a beta particle is an electron in nature. Fast moving, it's a beta particle, it is an electron in nature, and we represent it using a letter E and -1 like that. Then gamma rays are simply radiations. These are just rays of energy. Just that. Then alpha particles. What is the charge on an alpha particle? It is a positive. Beta particles are negatively charged. These ones have no charge. The mass, relative atomic mass. Remember, we said that alpha is a helium nucleus in nature. It is not a helium atom, but a helium nucleus. So we said that alpha particles are having a nuclear number of 4, so the mass number or the relative atomic mass is 4, so they are very heavy. Beta particles are less heavy, and then the gamma rays have no mass. Then penetrating power. How far can these ones enter into a material? How far can they penetrate material? So alpha particles are less penetrating. I'm going to describe this. I'm going to describe an experiment concerning this. Are less penetrating, like you saw in the video. These ones are more penetrating, and these ones can penetrate farthest. Can penetrate farthest. This one can be stopped with by just a paper. Stopped by a paper. Beta particles can be stopped by aluminium, and then gamma rays can be stopped by lead or a thick wall. Those are the differences as far as penetrating power is concerned. I'm going to show you a description of this like you saw in the video. Then ionizing effect. These ones are strongly ionizing. These ones are less ionizing. These ones have the least ionizing power. They have the least ionizing power. Then effect of an electric field. Alpha particles are positively charged. In case you pass an alpha particle through an electric field, they are deflected towards the negative. Towards the negative plate. I'm also going to show you an experiment concerning this. These ones are deflected towards the positive plate because they are negatively charged. And then since the gamma rays have no charge, they are not deflected. Then in in a magnetic field, alpha particles are deflected, beta particles are also deflected, and gamma rays are not deflected. Now, the directions of deflection of the alpha and the beta particles can be determined using the Fleming's left-hand rule. We shall not look at that right now, but just know that these two particles, alpha and beta particles, are deflected in opposite directions. Then fluorescence, in other words, what happens to materials when these particles fall on matter? So these ones can cause the matter to give off light, cause matter to glow slightly. So even these ones can do the same, cause matter to glow or to give off light briefly, and these ones also do the same. These ones also do the same. The speed of motion, these ones are very slow and they can only cover a short distance. These ones are faster, they cover slightly a longer distance, and then the gamma rays are the fastest. They cover the longest distance. In fact, they move at the speed of light, 3.0 times 10 power 8 meters per second. So let me show you brief experiments to tell the differences between all of these particles. Here, I'm going to look at penetrating power, electric field, and then effect by the magnetic field. I'm going to look at those three there briefly. So about the penetrating power of these radiations, alpha, beta, and gamma rays, I'm going to use this diagram here to illustrate this, and I'm having the source of these radiations here. So when these radiations, all of them, when they strike or when they fall onto a paper, just like that paper in your book, we can see that the alpha particles don't go through, but beta particles and gamma rays pass through, as seen there. And still, when the gamma and the beta particles meet a sheet of aluminium, we can see that the beta particles are stopped by aluminium, they don't go through, but instead the gamma rays go through that. And finally, when the gamma rays fall on a lead container, a lead sheet, or a thick concrete, they don't go through, meaning that they are only stopped by lead or a thick material. So that is about penetrating power, meaning that alpha particles are less penetrating, beta particles are somehow penetrating, and gamma rays are the most penetrating radiations. Then how are they deflected in an electric field? An electric field is simply where you have the positive charges and the negative charges. For example, the negative plate and the positive plate. So if the radiations are incident into an electric field, we can see that the beta particles which are negatively charged are attracted towards the positive plate. So they are attracted towards the positive plate, they're deflected towards the positive plate. On the other hand, the alpha particles are deflected towards the negative plate. Why? Because they are positively charged. And another thing you can see here is that the beta particles are strongly deflected, while the alpha particles are not so much deflected. What is the difference here? It is about their mass. A more clear diagram can also be seen here from this diagram here. So we have the reactive source, which is held in a lead container, and the radiations are deflected as shown above there. So this one here can be like connected on the positive, and then this one connected to the negative terminal of the battery, like that. In the magnetic field, it is the same thing. All the beta particles and alpha particles are deflected. Beta particles are strongly deflected because they are light, and gamma rays simply go through, as seen here. So with this, we come to the end of the properties of these radiations here. So prepare for a quiz shortly. Likewise, gamma rays and X-rays also have differences between them. We shall look at X-rays later on. But the difference between the two rays is that gamma rays have a very short wavelength, X-rays have a very long wavelength, and the gamma rays are produced from radioactive materials. And on the other hand, X-rays are produced when cathode rays are stopped by matter. Those are the major differences between the two of those. So let's try to go through some of the applications of radioactivity. Is radiation or radioactivity really important to us? The answer is yes. It is very surprising that there are very many everyday uses of radioactivity. So these ones are categorized into medical, industrial, agricultural uses, as we see here. So the first case here is that what are some of the medical uses or some of the medical applications of radioactivity? So radioactivity is found to be used in radiotherapy. Do you know what radiotherapy is? Yes, in the treatment of cancer. That is, they use the gamma rays. Then it is also used to sterilize medical instruments. What is the meaning of sterilizing? In the villages, they normally simply boil water, then they put the equipments and they boil them. In other words, sterilizing is simply to kill germs on the medical equipment. Then they are also used, the radiation is also used to detect brain tumors. A brain tumor is an unwanted growth in the brain. It is just a malignant growth in the brain. Radiations can also be used to detect lung and heart problems. That is also another use of radioactivity. And lastly, radiation is also used to destroy germs. That is about medical uses. Then the industrial uses are also enormous. There are very many of them, and among them is that radioactive elements can be used to determine or to measure the rate of fluid flow in pipes. For example, in national water, how fast is the fluid flowing in the pipes? It can as well be used to determine the leaks, the cracks in the pipes, or even in walls of buildings. Radioactive elements can also be used to provide energy. You've heard of the nuclear energy that is producing electricity using radioactive elements. So it can be used to produce electricity. Radioactive elements are also used to harden polythene and petroleum. In other words, in the process of manufacturing plastics and even in the production of petroleum, some radioactive elements are good at hardening these. Another use is in food preservation, preserving food. Some radioactive elements are used as tracers. Tracers, for example, identifying the leakages in oil pipes. You can go more about this. They are also used in the measurement of the thickness of metals or metal sheets, even glass materials. They can also be used to determine the thickness of materials. How is it that Coca-Cola is able to tell that this is the level where the Coca-Cola products are supposed to be in the bottle? How do they determine that? They can also be used to do that work there. Another, the radiations. Radioactive elements can also be used as level indicators. Level indicators, like filling up that Coca-Cola bottle. So those are some of the industrial uses of radioactive elements and radiations. In agriculture, where do we find radioactive elements being useful? Number one, in case we want to come up with a variety of plants, we can use radioactive materials to change the nature of some plants and come up with new ones. Radioactive elements can also be used as tracers, in this case, especially in the study of uptake of fertilizers in a plant. For example, you can simply put a small quantity of radioactive element in the soil, together with, of course, the minerals and so on. And then afterwards, you study the uptake of those in a plant. So they are used as tracers. In industries, we say that they are used as tracers to locate leaks in underground pipes. So even here, we're also seeing this tracer here. They can also be used in the pest control measures. In case we want to get rid of some pests, we use that. And then lastly, the last use is carbon dating. Commented about this at the beginning. Carbon dating, for example, in case we want to determine the age of a fossil, we use the idea of what called carbon dating, and we say that we use what called carbon 14. Why carbon 14? Because this is a radioactive isotope of carbon. So about carbon dating, when an organism is alive, it takes in, it breathes in carbon dioxide, and in that carbon dioxide there is this isotope of carbon. So once that organism dies, it is no longer taking in carbon dioxide, but instead the carbon 14 in that organism starts to decay, and it decays by the emission of beta particles. So, in so doing, if you can determine the remaining amount of carbon 14 in that organism at a given time t, and we know the quantity of carbon 14 in a living organism of the same species of the organism, we can always use what called half-life to come up with the time for how long that material has been there. So that is what we call carbon dating. Describing some of those uses, we have detecting fire, making papers, detecting leakages in underground pipes, detecting cracks in pipes and in buildings. All those are industry uses. Sterilizing medical equipment, talked about that. Killing germs, detection of tumors in the brain, all those are uses. Then the dangers of radiation. We said that radiation or reactive elements, we said that alpha, beta, and gamma rays are forms of ionizing radiations. Ionizing radiations, and this is potentially lethal. In other words, it can lead to death in case you don't manage them very well. What are some of the dangers of radiation? So, some of the health hazards of radiations include they can cause blood cancer, they can cause burns, they can cause sterility, in other words, inability to produce. So they can also cause low resistance. They lower the immunity of bodies, low resistance to normal diseases. They can also lead to genetic changes in organisms. We call that one mutation. And they destroy body cells. And lastly, they can also damage the eyesight. So those are some of the health hazards, those are some of the dangers of radioactivity. And after having known all of those dangers there, then how do we overcome that? So radiations or reactive sources must be handled safely. And whenever you see this symbol here, just know that that is danger. Always protect yourself or run away. So in the laboratory, some of the measures that we take, always keep exposure times as short as possible. In other words, don't take long when exposed to radioactive materials. Always monitor the exposure with the film badge. In other words, in case you have a gauge with you, can always be with it to detect how much radiation is in that region there. Always label these radioactive materials clearly, especially in the lab. Label those properly such that no one comes and tampers with them. Store them in shielded containers. Always use the lead containers or containers made of lead. We saw the reason for that. And always wear protective clothing. Put on protective gadgets. And lastly, always use tongs or robotic arms to handle radioactive materials. Don't handle them with your bare hands. So I'm ending with background radiation. We've talked about ionizing radiation and its dangers. In other words, the alpha, beta, and the gamma rays. We also have what's called the background radiation, and this one is always around us. It's always around us, and it is not as dangerous as the ionizing radiations. So most of the radioactivity you are exposed to is in the form of the natural sources. For example, you've heard of the cosmic rays from the sun. Others do come from human activities, like for example from industries, the waste materials that you dump in the oceans, in the ground. All these ones sometimes cause the background radiations. So, with this, I come to the end of our lesson. Try out the exercise, the next part. See you.